section on the primal and another section on the dual. And COP here is a constrained optimization problem. Okay, so first we'll focus on the primal. This is a constrained optimization problem, and I've used my convention here, which we shall follow for the rest of this course. So minimize with respect to x, this is the objective function, f of x, which is a mapping from n dimensions to a scalar, subject to these are the inequality constraints. Gi of x is less than equal to 0. Inequality constraints, and h of j x is an equality constraint. So these are the equality constraints. And we define the Lagrangian in this manner. The Lagrangian function, or simply the Lagrangian, is L x lambda mu equals f of x plus summation lambda I gi of x plus summation mu j hj of x. And these lambdas are always greater than equal to zeros. So these GIs are the inequality constraints, and if you notice, GIs are less than equal to 0, all of them, and the lambdas are all greater than equal to 0, so that the product, each term of this summation here, is always less than equal to 0. If you want to write these as greater than equal to 0, then make sure that either lambdas here are less than equal to 0, or you can place a negative sign here instead. And mu j's are all unrestricted, so they can be anywhere between negative infinity and infinity. So this x here is called the primal variable, and the lambdas and the mu's are called the Lagrange multipliers or dual variables. I call this the scalar form because here the inequality constraints, these functions here, and for the equality constraints, these functions, g and h, they're all scalars, so their range is one-dimensional. And the lambdas and mu's are all scalars here. But I can write this COP in terms of vectors. So minimize, this is the objective function. The inequality constraint is now a vector function, g of x, and likewise the equality function, the equality constraint is a vector function, h of x. And so the Lagrangian is written in this manner. F of x plus lambda transpose g of x plus mu transpose h of x, where lambda, this vector lambda, contains all the Lagrange multipliers lambda I, and likewise mu here, this vector, contains all these mu j's. Okay, so this is the Lagrangian, and we define the feasible set as the set of all possible x's that do not violate any of the constraints. So for all I, gi of x is less than equal to 0, the inequality constraints are satisfied, and likewise hj of x for all j is equal to 0. In other words, the equality constraints are all satisfied. And always remember that this lambda here has to be greater than equal to 0. This corresponds to the inequality constraints. For the equality constraints, the corresponding mu, dual variable mu, is unrestricted. It can be greater than or less than infinity. Greater than or less than 0. Okay, so I define the primal function theta p of x. Theta p of x is the supremum of the Lagrangian with respect to the dual variables. And so I've expressed theta p of x explicitly in terms of the Lagrangian here, and then scalar form of the Lagrangian. So this is the definition of the primal function. And since I'm eliminating lambda and mu by maximizing it, it's only a function of x. Do you have any questions?
I'm really confused about the primal function. What is the meaning of primal function?
We'll get to that later. And actually, it'll all be very clear when we do some examples. Okay, but for now, in this lecture, we'll focus on the theory. And do you understand sup is the supremum? Now, the notation that I use is, if it returns a numerical value, then I write max. But if it returns a function like this here, because it's a function, then I write supremum. I don't know whether that's correct or wrong, but for years, actually for decades, I've gotten around using this notation. Okay. So this is the primal function. But shortly, you might be able to see what the good thing about the primal function is. Okay. So this is the constraint optimization problem again in terms of the feasible set. So minimize with respect to x. This is our objective function, f of x. And this is the constraint. X belongs to f, the feasible region, or the feasible set. F, the script f, represents the feasible set. Theorem 1. In the feasible region, the primal function is equal to the objective function. And in the infeasible region, the primal function is infinite. Okay, so theta p of x equals, so when x does not violate any of the constraints, then theta p of x equals f of x. And on the other hand, when x does not lie in the feasible set, at least one of these constraints is being violated. In that case, theta p of x is infinite. And remember what theta p of x is. So we take the Lagrangian, and then we maximize it over lambda and mu. And we are left with theta p of x because lambda and mu have been already taken care of. We've maximized it with respect to them. Okay, so this is what Theorem 1 says. Theta p of x is, in the feasible region, it coincides with the objective function, and in the infeasible region, it is equal to infinity. Okay, and we'll assume that f of x is bounded. So it can never be negative infinity. It has a lower bound. Otherwise, what's the point in minimizing the function?
It will always stay in the feasible set.
F of x, even in the infeasible region, we can assume that it's, for this explanation purpose, we'll just assume that it's bounded. It has a finite lower bound. Okay? So we'll highlight this because it's an important observation. And let's see the proof. So theta p of x is given by this expression here. Supremum, we are maximizing with respect to all the dual variables, lambdas and mu's. So this is the objective function, summation of lambda I gi of x. These are the inequality constraints. Gi of x has to be less than equal to 0. Otherwise, the constraint will be violated. And that's why lambda I is always greater than equal to 0. And each of these terms here in this summation, mu j is an unrestricted variable. It can be anywhere between plus infinity and minus infinity. And hj, for feasibility, all the hj's must be equal to 0. Okay, so this is the definition of theta p of x. And then we see that this f of x is independent of lambdas and mu's, so we can take it outside the maximization. So we are left with this supremum with respect to lambda I greater than equal to 0 and mu j unrestricted of summation lambda iji plus summation mu j hj. Now, even in the infeasible region, x violates some constraint. We'll still have lambda I being greater than equal to 0. Okay? So we'll examine the two cases separately. When x is feasible and when x is infeasible. So case 1 is when x is feasible. Therefore, all the gi's are less than equal to 0 and all the hj's are equal to 0. Okay, now this is, okay, so this is all the gi's are less than equal to 0, but note that, like I said previously, the lambdas are all greater than equal to 0. Now, if I take gi and lambda I, their product is always less than equal to 0 because lambda and g are of opposite signs. Now let's look at the hj's. All the hj's are equal to 0 in the feasible region. Therefore, no matter what the values of mu j is, mu j hj will always be equal to 0. Correct? Therefore, what can you say about this supremum of summation lambda igi plus summation mu j hj? These lambdas, you're trying to maximize with respect to the lambdas. And note that lambda igi of x is always less than equal to 0. So each of these terms is less than equal to 0. How would you maximize them? The lambdas, you're free to choose the lambdas as long as they're positive. So in order to maximize this part, we have to set all the lambdas to 0. Correct? And this side, they're all zeros anyways, so we don't care. Okay, so the supremum, the maximum of this is equal to 0. Hence, theta p of x is simply f of x plus this whole thing here, and this we just saw was equal to 0. So this is equal to f of x. So we just proved the first part, that when x belongs to the feasible region, then theta p of x equals f of x. The primal function is equal to the objective function. And so this is the first part. Next, we will consider the second part. Okay. Now here, case 2, when x is infeasible. It does not belong to the feasible region. So something must be violated. At least one constraint must be violated. Correct? And this constraint could be a gi of x, or it could be an aj of x. So if a gi of x is violated, we're just looking at the most optimistic case of constraint violation. One gi of x is violated. Okay, so that gi of x, for some I, gi of x is greater than 0. And lambda I is always greater than equal to 0. So what happens to their product? Their product is always greater than equal to 0. Correct? Now, theta p of x would be the objective function f of x plus supremum of lambda igi of x plus other terms. Now, what's the supremum of this? Noting that lambda igi of x always remains non-negative. It's positive or 0. Correct? How do we maximize this? Simply by letting lambda I approach infinity, plus infinity. Correct? In which case, this term becomes infinite. Okay, so theta p of x in that case, so when lambda I equals infinite, this term here becomes infinite, and so theta p of x becomes infinite. If a gi of x is violated, then theta p of x becomes infinite. Okay. Any questions? You came a little late, but are you able to follow? Okay. Okay, so this is second case, but when a gi is greater than 0. One of the inequality constraints is violated. Now let's look at the other case when, well, it's still case 2. X is infeasible, but the other sub-case or sub-situation where an H equality constraint is violated. So suppose an Hj is violated. So in other words, it's an equality constraint. Violating this equality constraint implies that this equality doesn't hold. So Hj can be positive or negative. It's just not 0. So Hj is not equal to 0, and mu j, remember, can be of any sign. It can be plus or minus. What we do is we let mu j acquire the same sign as Hj, which is not equal to 0. If Hj of x is positive, then we let mu j become positive. If Hj is negative, then we let mu j be negative. Therefore, what happens to their product, mu j, Hj, since they're both of the same sign, it's strictly greater than 0. Okay, this is Hj is not equal to 0. Okay, so Hj is a non-zero quantity, and so mu j Hj is strictly greater than 0. Now, theta p of x is now f of x plus, now we maximize with respect to mu j, this mu j Hj. What happens? How do we maximize this? This is always greater than 0, as long as mu is not 0. Okay, and we are free to maximize with respect to mu j. All we have to do is let mu j be either plus infinity or minus infinity, depending on the sign of Hj. So mu j equals sine of Hj times infinity. Okay, and then what happens to the this becomes infinite, right? So it's unbounded. Therefore, mu j Hj is infinity, or theta p of x is infinity. In other words, if an Hj is violated, we see that theta p of x becomes infinity. Okay? So graphically, this is what it looks like. So it's one-dimensional. So this is f of x. This blue curve is f of x. And this green region is the feasible region. And f complement, this and this, the left and right hand side of this feasible region, they are infeasible in this illustration. So this is theta p of x, the dotted red line. So in the feasible region, it coincides with the function f of x. The objective function and the primal function are identical. But in the infeasible region, what happens? It becomes the theta p of x, the primal function becomes infinity, unbounded, both sides. Okay. So this is what we just saw. Theta p of x is, what we do is, this is the Lagrangian. It contains the primal and the dual variables, and we are getting rid of the dual variables through maximization. And we just noted that theta p of x is f of x in the feasible region and unbounded otherwise. So This is the primal problem. Minimize theta p of x. Okay. And instead of trying to address the original COP, which has an inequality constraint and an equality constraint, we can minimize theta p of x, which is unconstrained. So the primal problem removes constraints. A worked out example will make things absolutely clear. Okay. And we can readily see that the solution of the primal problem is the constrained optimum. Okay, so when we minimize theta p of x, we are bound to remain in the feasible region, right? Otherwise, theta p of x becomes infinite. So the solution of the primal problem is the same as the constrained optimum. Yes?
I'm not able to understand this thing like the primal problem removes the constraint. Isn't it the Lagrangian equation that helps to make an unconstrained equation?
Yes, but then we are removing, from the Lagrangian, we are removing lambda and mu.
Yes.
So again, this is just a function of x.
Okay.
Okay, and it's just our good luck that this is theta p of x. So instead of f of x, we have this is theta p of x. We can choose to minimize theta p of x instead of f of x. And this is, the optimum x star of the objective function, which is the same as, we'll call it theta p star. So this is our corollary here. The solution of the primal problem is the constrained optimum. In other words, x star equals arginf of theta p of x, which is arginf of, with respect to x of the supremum with respect to lambda and mu of the Lagrangian. Okay. Note that what we are doing is we are taking the Lagrangian and then we are maximizing over the dual. And then we are minimizing over the primal. Okay. And instead of trying to minimize the objective function, f of x, within the constraints, we choose to minimize theta p of x without any constraints. And this is our notation. X star is the optimum of both the objective function, the minimum of the objective function within the constraints, which is also the minimum of the primal function unconstrained. Okay, and we will call that the value of the objective function, the same as the value of the primal function, theta p star. Okay, so this is x star and this is theta p star. Now here it's it's in the boundary between the infeasible and feasible, but that depends on the shape of this. This function here. The minimum could have been somewhere else. Maybe it would have been a cup shape here, going down all the way here and come here. In which case, this point would have been x star. Correct? So this is basically the corollary. So we examined the primal function, and then we saw that we could simply minimize the primal function without bothering about the constraints. In an actual problem, you'll have to formulate the primal problem depending on how it's cast. You'll have to do some algebraic manipulations. Okay, duality theory now. So this is again the constraint optimization problem. F of x we want to minimize. That's a mapping from n dimensions to one dimension. And we have this vector function gx is less than equal to 0. The inequality constraint, that's a mapping from n dimensions to L dimensions. And these are the equality constraints, or a single vector equality constraint. H is equal to 0. That's a mapping from n dimensions to m dimensions. L is the number of inequality constraints, and m is the number of equality constraints. And this is how we define the Lagrangian. Always remember that the lambdas have to be greater than or equal to 0. And this is the feasible set. F is the feasible set or feasible region where none of the inequality constraints or the equality constraints are violated. Now we'll define the dual function. Just to recall, how did we define the primal function? We first, here you see there's a minimization, right? What we did, the duals, we took the Lagrangian and we tried to maximize the Lagrangian with respect to the duals. We're doing the opposite of minimizing, okay, when handling the dual variables. Now, the dual function is this. The dual function is a function of the dual variables, lambda and mu. And here, we're minimizing, taking the infimum of the Lagrangian with respect to the primal. Okay, so the Lagrangian, when we were trying to eliminate the duals, we did a maximization. But now we are doing a minimization, same thing as the original constraint optimization problem. So this is what we want to minimize with respect to the primal variable x. So this is the infimum of this whole thing. Okay? And theta d is a mapping from L plus m dimensions to odd a scalar, because we have two sets of variables. This is an L-dimensional vector, lambda, and mu is a m-dimensional vector. Okay, any questions so far? Okay, so this let's highlight because it's an important definition. And I can rewrite the feasible set in this manner in terms of vector functions g and h. Okay. Theorem 2, the dual function is concave. Okay, now let's recall what the definition of concavity is. Well, we've seen the definition of convex function, and the definition of a concave function is just its negative of that. So this is, this red line here, curve, is a concave function, f of x. Okay, so we take 2 points, x1 and x2, and so this is f of x1, this is f of x2. This straight line segment joins x1 comma f of x1 with x2 comma f of x2, and we divide this in the ratio 1 minus alpha to alpha. So this point here is alpha f of x1 plus 1 minus alpha f of x2. So this is a linear combination of the function. And again, this is alpha x1 plus 1 minus alpha x2. This point here is a function of the linear combination of the arguments. So this green here represents the linear combination of the function, and this f here is the function of the linear constraint of the linear combination. Okay, and so we will prove concavity with respect to lambda and mu separately, and you can see the one-to-one correspondence, the blue and the green here. So when we are trying to prove concavity with respect to lambda, we'll just ignore mu. Okay, so this is a function of the linear combination of the lambdas, and this is the linear combination of the function of lambda 1 and lambda 2. Okay, so you see the correspondence here, and this blue has to be greater than equal to the right-hand side, the green, as you can see here, for this function to be, theta d to be concave. Okay, this x here is not the primal variable, okay? It's just an arbitrary x in this figure. Okay, so we will prove concavity with respect to lambda only, and the concavity with respect to mu is very similar. Okay, so this is the important observation, and so we'll proceed to prove it. So lambda is equal to alpha lambda 1 plus 1 minus alpha times lambda 2. Okay, so the left-hand side is equal to infimum of this, which is equal to the infimum. Theta d is an infimum, right? The function is theta d, the dual function, is defined as an infimum of this. Okay, and now lambda, we can divide it up into alpha lambda 1 and 1 minus alpha lambda 2. So this lambda here, I have divided it up. Okay, and then what I'll do is, this f of x, I will split it into alpha f of x and 1 minus alpha f of x. And I'll do the same thing with this second term here. Mu transpose h of x, I've again divided it up into alpha mu transpose h of x and 1 minus alpha mu transpose h of x. Okay, and then what I'll do is, I'll lump all the terms containing alpha on one side and all the remaining terms containing 1 minus alpha on the other side. So this is what I have. Infimum of this whole thing is theta d of lambda mu. Okay, where lambda is alpha lambda 1 plus 1 minus alpha lambda 2, this lambda here. Are you guys with me? Okay, so this is where we are. So these are the terms containing alpha, and these are the terms containing 1 minus alpha. I'll take alpha common and 1 minus alpha common. Okay, so what do I have here? When I take alpha common, I have f of x plus mu transpose h of x plus lambda 1 transpose g of x. So this is basically the Lagrangian Lx lambda 1 mu, correct? And this here, these terms containing 1 minus alpha, likewise, is 1 minus alpha times lambda x lambda 2, because we have lambda 2 here, mu. Okay, so this is what we land up with. And then this is greater than equal to alpha. I just took alpha outside the infimum. What I've done is, this is infimum with respect to only this first term, and then 1 minus alpha I took outside. What remains is infimum with respect to x of the second term. Why does this inequality hold? Because if you take any two functions, just ignore the weights, or maybe the alpha and 1 minus alpha are part of the functions f and g. Okay, so the minimum, when you're trying to minimize the sum of two functions, f of x plus g of x, you land up with a bigger value than when you try to minimize f of x and g of x separately and add them up together. It's just common sense, right? And so this is where we are. And so this is equal to alpha theta d of lambda 1 mu plus 1 minus alpha theta d of lambda 2 mu, because by definition, the infimum with respect to the primal variable x yields the dual function. Okay, so we just established concavity with respect to lambda. And the proof for the concavity with respect to mu is along the same lines, and so I've omitted it. This you can prove just by following these steps. Okay, but another important observation. An equality constraint can be viewed as two inequality constraints. So if we have an equality constraint like this, hj of x is equal to 0, we can split it into two inequality constraints. hj of x is less than equal to 0 and negative hj of x is also less than equal to 0. In fact, in some places, some textbooks, you'll find that the equality has been completely ignored. It just assumes that the constraint optimization problem has only inequality constraints. Okay. So you'll come across such textbooks or papers where you don't have a separate set of equality constraints. Everything is assumed to be inequality constraint. Okay? So the dual problem. We saw the dual function, and an important property of the dual function, theta d, is it's always concave, regardless of whether the original objective function f of x is convex or not. The dual is always concave. That's an important observation. Okay, now what's the dual problem? Maximize theta d with respect to lambda and mu. Okay, and we are doing this maximization with respect to lambda and mu. These are the dual variables. So lambda star mu star equals arg sup of theta d lambda mu. And again, lambda has to be greater than equal to 0, remember. And this is equal to theta d of lambda mu is infimum of the Lagrangian. So what are we doing here? In the primal problem, what did we do? We first minimized with respect to the duals, and then we maximized with respect to the primal. Correct? Here, what we are doing the opposite. We are first minimizing with respect to the primal, and then we are maximizing with respect to the dual. Okay. You see, we are doing the maximization and the minimization in opposite sequences. Okay, that's another important observation.
But if we are doing a minimization in x, why is the syntax of infinity? If we are minimizing with respect to x, but we are there is I and f infinity.
Because the Lagrangian will be will be unbounded. It will be infinity when x is infeasible.
Okay.
Right? And so we are automatically constraining ourselves to the feasible region when we're doing the minimization. Same thing as doing as this function, right? It coincides with the objective function when we are doing the minimization. So, okay, so this is what we do. So, And the actual value of theta d at lambda star mu star is theta d star. Okay, so now here's what we have. So x star, this is arginf of theta p of x. So this is, we are doing the minimization with respect to of theta p of x, which is minimization with respect to x of the maximum with respect to the duals. This is just what I was saying. This is the Lagrangian. We maximize over the dual variables, and then we minimize over the primal variable. Okay, and that was theta p star. And this is just the opposite. Arginf of sup of the Lagrangian, this is arg sup of inf of the Lagrangian. Okay, now what's the relationship between the two? Okay, we will shortly see that this inequality always holds. This is theta d lambda mu, right? And this is theta, this is the maximum of theta d lambda mu. And theta p star, this is the minimum of theta b, theta p x. So the theta d star is always less than equal to theta p star. And under certain circumstances, when certain conditions hold for the constraint optimization problem, one of them, this is a sufficient condition, it's the Slater's condition. In that case, theta d star equals theta p star. Okay, and let's see why. So this is the dual problem, right? We maximize the dual function over lambda and mu, and this is what we get. Weak duality always holds. The supremum of the dual is less than equal to the infimum of the primal. Okay, this theta d star is always less than equal to theta p star. Why? Because, let's see why. Infimum of the Lagrangian is always less than the Lagrangian, right? Infimum with respect to x of Lagrangian is less than equal to, for any variable, for any value of this variable x of the Lagrangian. Correct? Now, all I do is take the supremum on both sides. So, supremum of this is always less than equal to supremum of this. Now, this is the, for all values of x, this inequality holds. Correct? In particular, it will hold even when we minimize with respect to x. And so this is our proof. It's a very common sense proof, actually. If you first maximize, then minimize, as in the primal, so this is the primal, right? So if you first maximize, then minimize, you'll always land up with a higher value than when you first minimize, then maximize. Okay, and hence theta d star is less than equal to theta p star. Now, theta d star is what? It's less than equal to theta p star, but this is the maximum of the dual, right? So the maximum of the dual, and what's theta p star? It's the minimum of the primal, right? So in other words, for all values, this entire function, theta d, always is below theta p, right? And so this is the next theorem. Theta d, the value of this function, no matter what lambda and mu are, lambda has to be greater than or equal to 0. Theta d is always less than or equal to theta p of x. And this is the proof, which is common sense, actually. Okay, and so the difference between them, theta p star minus theta d star, is greater than or equal to 0. This is called the duality gap. Okay, and constraint qualifications. So under certain conditions, such as Slater's condition, which we shall examine shortly, if there are these any constraint qualification, under those circumstances, the duality gap is equal to 0. So the primal and the dual touch each other. Okay. So
at the optimum point, the primal function will become equal to the objective function?
yeah.
And how about dual function?
It will be less than, well, if strong duality doesn't hold, then it will always stay below.
Okay.
Okay. In fact, this lambda star mu star, it's a slight misuse of notation because the usual convention is when strong duality holds, then the optimum is x star lambda star mu star.
Yes.
Okay, so don't get confused. In some places, that's how it's introduced. It's only when the touch, then that point is called x star lambda star mu star. But just for explanation, I'm using this. I just found it more convenient to explain it this way.
Even the star is also used in some textbook for the optimization point.
Optimum.
Optimum point. Yes.
Exactly. Yeah. So, and it's also used for other equilibria too. Nash equilibrium. I work a lot with game theory.
Okay.
Nash equilibrium is also represented with a star, if you know what Nash equilibrium is. Anyway, so this is weak duality, which holds by default, and this is strong duality. And this is the duality gap. Strong duality is when they're equal, or when the duality gap is 0. So this is Slater's condition. So x naught, there exists a point x naught such that the inequality constraints are inactive. So in other words, this less than equal to, it's a strictly less than. Okay, it's not at a boundary of one of the inequality constraints. This x naught is strictly in the interior of the feasible region with respect to this. Okay, the inequality constraints. And of course, the equality constraints, any deviation from 0 would violate the equality constraint. So Hj of x naught equals 0. Oh, I should have written x naught equals 0 here. Okay, so this is Slater's condition. If the objective function and all inequality constraints are convex, and all equality constraints, Hj of x, are affine, that is linear plus a constant, and Slater's condition is satisfied, then strong duality holds. Now, this is a sufficient condition. Even if Slater's condition is not satisfied, strong duality could still hold. My lecture notes, if you see my lecture note, well, I haven't uploaded it yet, but because I have to edit it to add some of the other stuff, that's why I have to rewrite something. So that's why. But when I upload it, I'll include an example of a function where the Slater's condition is violated, but strong duality still holds. Okay, so this is a restatement of the condition for strong duality. F is convex, each GI is convex, and this is what I meant by the equality constraints are affine. H of x can be written as ax minus b equals 0, or ax equals b. Okay, since I want to have a 0 on this side, I'm writing ax minus b. And such that there exists, this is the symbol for there exists, an x naught such that gi of x naught is less than 0 and hg of x naught is equal to 0. Sorry, this should be x naught here, x naught here. I just copy pasted. Then, if these conditions hold, then theta p star equals theta d star. Okay, and this is another thing that we should remember. You can see when you're actually dealing with these things that it's very easily satisfied. Okay, or there are other conditions. So in most cases that I've come across, strong duality holds. Excuse me. Okay, so this is the primal problem. This is the primal function here, theta p, and this is the x-axis of the primal variable axis. This is theta p, well, theta p star at the minimum of theta p. Okay, and this is the dual problem, and this is, so this is orthogonal to this. Have this axis, green line here, just represents both lambda and mu. Okay, so this is theta d lambda mu. The red curve here, this blue is theta p of x. Now, this is theta d star. Okay, and so this difference is the duality gap. And when they touch each other, so this somewhere it'll coincide with this. That's called the saddle point. And like I said, the very common convention is only when they touch the saddle point, that's the point where which you call x star lambda star mu star. Okay, now why use the dual instead of the primal? Like in support vector machines, we always use the dual. Okay, and are you know support vector machines, but you don't know the derivation, right?
No.
Okay, now I'll, next lecture, what should I do, or maybe next Thursday, what should I do, what examples do you want, I'll ask you. Okay, so why do we use the dual sometimes? Because it's very often algorithmically easier to solve. Okay, and it's always concave. Okay, suppose the primal is not convex, okay, but the dual is concave, and suppose the duality gap is 0. Then why not solve the dual instead of the primal? Support vector machines, it happens that way. Okay, it's better, easier to solve the duals.
It means that by using the dual function, we can find the global maxima, global minima?
Not global, constrained.
Okay.
It's always under the constraints, right? Okay, so yes, to answer your question, just eliminate the word global. So from the dual, we can find the minimum of the objective function.
Is it because it will have multiple minima and maxima? That's why we are constraining it?
No, it's just the nature of the problem. It is a problem, and it has, we don't care what it has, whether it has multiple minima or not. We don't care if it's a convex function or not, but we want to minimize this function with respect to these constraints. And you'll come across such problems all the time. Okay. So, and in support vector machines, the constraints are actually quite simple. They're all linear. Okay. And so why choose you have the kernel and blah, 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 and sort of that. choose the dual. Okay, so it's always concave. So if the duality gap is 0, you'll always hit the optimum point, right? The saddle point. Now, even if the duality conditions, if the under some conditions duality gap is 0. Now, even if the strong duality doesn't hold, it might be a good idea because it tells you what a good lower bound of the constraint optimization problem is. Okay, and suppose you're using a more complicated algorithm to address the primal problem. So let's say gradient descent within the constraints. Okay, so you're applying it and it'll tell you how close you are to the optimum by simply examining the value of theta d star. Okay, so these are the reasons why we use the dual form. Okay, so this is strong duality, and so it's with respect to lambda and mu, you hit a maximum, and with respect to x, you're at a minimum. So this point is the saddle point, x star, lambda star, mu star. Why it's called a saddle point? Because it looks a lot like the saddle of a horse. Okay, so we still have some time. So any questions? Please feel free to ask. Okay, but so you see the point. Once we look at some examples, then it'll be clear.
Yes, because I'm not still able to digest that. How can I imagine the dual function and the primal function in the context of objective function? We have objective function and the constraints, and from those things we are developing two more functions. One is the primal function and one is the objective function, dual function.
Yeah. I wish I had a slide on that, but unfortunately I don't. Okay, but if you go to my YouTube videos, I have examples there. Okay, I'll provide the link, and then you'll see. What I will also do is, maybe this is what what I'll do. I'll upload examples separately before completing the lecture notes. I have to write a whole lot of stuff. Okay. Okay then. Any other questions or issues? Okay. कॉफी पीना है आप लोगों को? कॉफी पीना है? Let's all go.